Welcome to another video. This is Rashid speaking. We have been looking into combinational circuits. In the last video, I gave you an example of that. And today we will look into a few other things still related to combinational circuit. Before I go further, I want to highlight some of the terminologies. We used them in the last lecture, but I still want to mention them again. Okay, complement. What is complement? And complement, like, remember we had a term B, like an input B using input F, and just this was a complement inversion on top of that. Okay, then minterms. If you remember, we had these ones. So this is a minterm, and this is a minterm. Okay, sum of minterms, and again you can see a minterm and then minterm, and this is a sum of that. Orders of operations. So in a sum of minterms, you first do ANDing together, and the result of the two or more ANDs, I mean there could be more, then you OR them like here. So the order operation is first these two need to be done, then this, not like these two need to be OR and then AND. Okay, it's pretty obvious, but just want to make sure. You probably be thinking, okay, what if instead of multiplying them or ANDing them and then adding them or ORing them, why not we did something like, let me use the same red pen. We use something like this. Which is opposite of it if you look at. You are adding them, means ORing them, and then it's supposed to, so the first stage is OR, the last stage is AND. That's what I meant. Okay, I don't know if you had that question, but that is possible. That is totally possible, and that is called product of sums. So you have sums, then you make product. In which scenario you do it? So I'll already do a few things here so that it takes less time during the video. I wanted to make quicker videos so you can understand these concepts quickly, because I totally believe these are very simple concepts. That's what I love about digital design. Once you transfer something in 1 and 0, things become easier. It's like a higher abstraction. Just seeing things as 0 and 1 makes a lot of sense, and operations become much simpler. In real world, things are, of course, more complicated, and we will look at them with an example of when we look at the transistor level. But I think the most of the digital transformation that is happening in the chips is at digital level. So once you learn these things, you really build a pretty solid, pretty good concept. So what we did, if you remember this example in previous videos that I've been taking with alarms, fire alarm, intruder, and maintenance, those are the inputs, and based on those alarms with certain priority, with fire highest, then intruder, and then maintenance, we turn outputs alarm to fire brigade, alarm to police, alarm to maintenance person in the company. So based on certain combinations, we turn certain signals higher. So alarm goes on when fire alarm is 1. Then others don't care. Doesn't matter what the value is 1. Now look at the maintenance output. Whenever an intruder is 1 and fire is 0, it doesn't matter what's the value of M. So we get alarm. So basically what we wanted to get was AP to be high, alarm goes, when for these combinations. And that's where we build this circuit. And we wrote minterms based on this. When the output becomes true or high, and in that case, we're just picking those minterms And to make it high, we just AND them together. And then OR. OR means either this combination gives you 1 or this combination gives you 1. But we can also do an opposite way. In what we call this thing was max kind of way. By the way, this is I just put an example. It's not correct. So you will see here. In the max term, what you do is you write the combination for which that output is 0. So for example, in our picture, remember I drew that, okay, these outputs are driving a circuit with a bulb. So maybe the bulb switches on with 0 there. Some sort of circuitry that switches on with 0. So instead of generating ones, we generate a circuit for zeros. In that case, and this is just an example, in that case, we will use this approach. Sorry, I'm going back and forth. Product of sums. For example, let's do that. Let's do it actually here because we have everything here. This is the table. So what we're gonna write, so let's this one. And now here is an interesting thing about this scenario. So what you do is F. Now we will remember here in this case we did F dash I. Okay, let's write that here. That's easy, much easier. So in that case it was AP F dash complement I and complement. The combination was again F has to be 0, I has to be 1, and doesn't matter. Actually that's a bit, don't care, but that's okay. Let's write that. Okay, all right. So basically what we were picking was the one, if F gives 0, it will be, to make it 1, this need to be inverting. This need to be inverting. This need to be inverting. Only then this becomes 1 because these are ANDs. AND will be, output of AND will be 1 if all inputs are 1. If one of them is 0, output will be 0. So if you want to write in terms of AND and want to make output of AND 1, then you have to invert these in such a way when F comes as 0, this thing gets F dash becomes 1. M dash becomes 0, sorry, M becomes 0, F dash or F prime or F complement become 1. Now in this situation it will be different. It will be like again A, B, let's call it max. Now our situation is we want to make for this we want to make output is 0. So for OR, when output is 0, everything has to be 0. Only then output is 0. If one of them becomes 1, it will make the output from output will go from 0 to 1. So you really want to make every input 0. Okay, let's, for this case, how we make output 0? F, I, M. Actually, they all come as is. So you do this. Again, it's OR. You're ANDing because you want to make sure that the output is 0. What is the, I'm going down. There's an OR. Oh, I can remove that. Okay, what's the next one here? F, I 0. M is 1. Now we need to make it 0. So what we do is, again in this case is 0 when F is 1, that will make it 0. So you see, oh sorry, this one. I'm so used to the product of sum of minterms that I'm also making a mistake. Okay. Now, when the question is, you probably be thinking, why we do one or this one? When we do this method, when we do this method. Typically, this is used more when you have fewer ones. You can see there will be a smaller hardware with this one. Here you have this. In this case, probably not that big, but in circuits, when you see a fewer ones, here you have 3, so you are definitely using one additional. And if you inverted once, you're probably not using that, but still you have another wire coming in. Your last gate will be 3. Sorry, still drawing that thing. And with 3, and there is R. There's R, F, I, M, F, I, M bar. This one's F. So you are using a bigger, this gate, a 3 input, as opposed to here your 2 input. And later on, when we look into CMOS and build circuits with 2 input OR or 2 input NOR or NAND, you will see that there are more transistors used in this. So by going with this one, it's still simpler than this one. So typically what I was saying is, if you have fewer ones, you better go with this method. If you have fewer zeros, you better go with this method. That's how you decide. But whether you generate output 0 and for others it's 1, or you generate for certain combination 1 and for that it's 0, it doesn't matter, right? Does it? Because what will happen when these combinations come, this circuit will generate 1. So all you want it, I don't know, maybe I put a wrong comment earlier on when I said, okay, depends on whether you want to generate signal 0 or 1. But you can have the same circuit as the output of product of sum of I'm getting confused, sum of these terms or these terms, they will generate the same combination. You're just figuring out which one you use to create this logic, and you pick the one that gives you a simpler result. Okay, all right, so I think we covered these terminologies. Few other things I want to get into. Okay, simplifications. I told you in previous video that I will present a couple of topics on that. There, as I said, hardware, you want to make hardware simple. Simpler hardware generally means less devices, which means smaller area, which also means lower power. Correct? In that case, it's important that you simplify your circuit. Now, some of these simplification methods that I'm telling you, if you're a physical design person, you're not going to do those. Synthesis tools are going to create those simplifications for you. So if you ask me, are there applications of these yourself? Probably not. But at the same time, it's good that you know them. You can come across some of the ECUs, engineering change orders, where you modify the circuit yourself, and then you can simplify it. But again, that's not required. I think even some of the tools will help you with that. But having that understanding how we can simplify things is nice to have. Okay, so you're not going to use most of it, probably never, but nice to know them. For that reason, I will go a little bit quicker on these ones. We use some of these theorems to simplify equations like this. Look, even in this equation, you can see that f dash and I are common. Okay, so we can simplify this equation a little bit further. But let's go through these theorems, and you see based on that, you can get some ideas. Always go with 2 sets, as you have seen. there is sum of minterms, there's a product of maxterms. We'll do an and, you can have or operations, you can have both sort of things. So we'll look into both. So B here is just an input. It could be an F, I, and M that we look in the previous example. So when you AND 1 with any input, an input can change, but when I put B, it means it can be 0 or 1. When you AND with 1, you basically saying that it's simply as B. And here, let me give you some examples. I don't want to spend too much time, but I do want to spend a little bit of time so you understand that, and I'll wrap that up. So for example, it's an AND gate. You have B coming in and 1. So if B is 0, it will make this circuit output 0. If B is 1, it make output 1 because other side is 1. So in that case, you are just wasting an AND gate there. This circuit means you can simply remove AND gate and propagate your B. You don't need this thing. There are transistors inside that are taking current, that charging, discharging, going, which also creates power. And if it's in the circuit, it's also creating a delay. In that case, you don't need it. Simply just replace it with just route this thing to the output. Similarly, look at this case. When this is B and you put here as 0, putting 0 here means output will be 0. Doesn't matter what B is. So in that case, why you are wasting an AND gate? You simply ground that. Whatever that input is, you simply ground because it's always be 0. So techniques like these, you can really use to simplify circuit. Okay, B with B, you are wasting an AND gate because output will be. If you have a B and with the inverse of B, you can also say that will all be 0 because if this is 1, the other will be 0. If this is 0, this is 1. If both are 1 and both are 1, let me draw this. I don't want to confuse you. What this means is you get B, and on the other side you have an inverter, and then it goes to B. So if B is 0, this is 0, this is 1, this is 0. B1, this is 1, the other one is 0 because there's an inversion happening. Output is always 0, so it doesn't matter. Your homework is to prove this for this other scenario for OR. It's the same thing. Some theorems. Some more theorems. You must have seen these. These are pretty obvious things. I know we have been studying this in Boolean or in algebra, and basically same thing applies in this case. That's the beauty of 1 and 0. You can use a lot of things from Boolean equations from algebra. Okay, so, and I'm listing things here for and. You can create the same theorems for R. Mean when you have a situation with B and C are Ring. Here I'm just assuming they're always ANDing. And those are the two combinations that's going to happen. As we previously seen, you are doing either sum of minterms of product of maxterms. So you're doing AND or OR operations. That's why I'm presenting two scenarios. Whether on AND you have B at the top, C at the bottom, or C at the top, yeah, it doesn't matter. You B connect here C, or you have C B, doesn't matter. Whether you AND B and C and then output of that with AND, or you first AND C D then output, doesn't matter. B and C they're AND, and then B and D are and then you OR them. It's the same as you OR C and D, and the result of that you AND with B. Whether you OR B and C, and if you AND it with B, it's the same as B. And maybe take homework. Draw these AND gates like this that I did, for example. B, C, and then you AND with B. And prove, is it really always going to be the same as this or not? So that's your homework. I will skip that. And as I said, as a physical design person, you're not going to do it. If you're a custom digital circuits where you're drawing those circuits in a custom way, then you will probably be doing these type of things. It's a good one. Inversion of C, if you AND them, then OR them, you'll get B. Similarly, this is a long one. An important, very important one is this. If people have already studied digital design, you will see De Morgan's. I joined it. But this person, Augustus De Morgan, a British born in India between, he lived 1806 to 1871. Just wanted you to remember this law with this picture. It's an important one. It's very simple but important. And what it says is, let's say you have product, an input, but a B0 and another input B1 and B2 and so on. If you want to invert that, I think I should have called it, let's say this is Y. And let's say it's a huge AND gate, B0 count, B1 count, B2 count, and say I need the same, but I need an inversion of Y. Maybe you need to invert Y, but you want to write an equation for that. I mean, you can put an inverter there, right? As you say, I don't want to put an inverter, I just need as input some different, I need an OR gate with certain combination, and this time it will be Y dash, because this will basically written for 0 and zeros. This is written for 1, but again the result will be similar. What happens is when you do this, you just invert each of them and you OR them. So what you will have will be B0 inverter, B1 inverter. Or another way, I think I put an example, it is a good one. So you have AND Y is equal to AB. When you inverse it, complement of Y, you can write those equations. Writing those equations in these forms is easy because based on this you can create new circuits. You can play a lot with these ones. You can use different theorems and other simplifications. So this is just a continuity of the previous concept. Not a big deal. What you do is you come up with this one, that means an R, and then you have inputs inversion happening. Sometimes we also use this bubble method. That also means A inverter B1. I just want to take you through some of these things because this is not something you're going to use again and again. And I forget that. And it's fine you forget that. But it's good to know some of these terms when you're asked questions anywhere. You don't feel like an alien to those. Another one, it's a key one actually used in simplification. So the thing is, if you have a combination such that B is another input, could be F, could be anything. But if you have a situation where this input A is multiply means an and this is like, there's an AND gate with B and A, and what's happening? Or with this I'm saying, but inversion. This whole thing, you can simply you can route it to the upper. You don't need to waste these two gates. You don't need to waste silicon area with these two gates, which is gonna take up area, which is gonna also take up more power. So the key thing is, since A, all right, 1 second. I think I wrote something incorrect there. Let me fix that. So you have B, oops, here, right? Now it makes sense. Yep. All right. So with this method, now you can have this, making sure you can have, this is another tool for you to simplify things. So hopefully you have learned some new things during this video. If any questions, IM me on LinkedIn, give me your feedback, or you can also comment on YouTube. Thanks so much. See you in next video.